Containerized Code, a hands-on guide to Docker for everyone. Chapter 1, Welcome to the Container Revolution, Why Docker Matters. Have you ever heard a developer exclaim, "But it works on my machine"? Perhaps you've even uttered it yourself. This seemingly innocuous phrase is, in fact, a whisper of a very common and frustrating problem in the world of software development and deployment. Applications often behave differently or fail entirely when moved from one computer to another, even if those computers seem to be configured identically. This seemingly simple issue has plagued engineers for decades, leading to wasted time, missed deadlines, and a boatload of frustration. Before we dive deep into the world of Docker, let's unpack this problem a little further and understand the challenges that software developers and system administrators faced on a daily basis. The problem before containers, the works on my machine dilemma. Imagine you're building a complex application. It needs a specific version of a programming language, several software libraries, a particular database, and perhaps even some command line tools. As a developer, you carefully install all these dependencies on your local machine, tweak the configurations, and finally, your application hums along perfectly. Success. Now you hand it over to a colleague, a tester, or deploy it to a server. Suddenly, it breaks. Why? Dependency conflicts and DLL hell. Your application needs version 2.0 of Library X, but the server already has version 3.0 installed for another application, and the two versions aren't compatible. Or perhaps a shared library on the system is updated, unexpectedly breaking your app. This was famously known as DLL hell in Windows environments and exists in various forms across all operating systems. Inconsistent environments. Your development machine might have a certain operating system version, specific environmental variables, or network configurations that differ subtly from the testing environment or the production server. These minor differences, often overlooked, can lead to major headaches. Slow onboarding for new developers. When a new team member joins, they spend days or even weeks just getting their development environment set up correctly, installing all the right tools and dependencies, and wrestling with configuration files. This is time not spent on building software. Challenges of application deployment and scaling. Deploying an application to multiple servers reliably is a painstaking process. You need to ensure every server has the exact same software stack. If you need to scale up by adding more servers, you have to repeat this manual, error-prone process. Updates become nightmares, and rolling back to a previous version can be even worse. This fragmentation and lack of consistency created a deep chasm between different stages of the software lifecycle, development, testing, and production. What worked perfectly in one stage often stumbled in another. Introducing containers, the shipping container analogy. To understand how Docker solves these problems, let's consider a real-world analogy: the international shipping container. Before shipping containers became standard in the 1950s, cargo was loaded onto ships in a chaotic mix of crates, barrels, and sacks. Each piece of cargo needed individual handling, making loading and unloading slow, expensive, and prone to damage or loss. Then came the standardized shipping container, a uniform, sealed box. It didn't matter what was inside, electronics, clothes, or toys, as long as it fit within the container. These containers could be stacked efficiently on ships, trains, and trucks, moved easily by cranes, and transferred seamlessly between different modes of transport. The revolution wasn't just about the box. It was about the standardization of the box and the infrastructure built around it. In the software world, Docker containers are precisely that: standardized, self-contained packages for your software. Just like a physical shipping container can hold anything from electronics to furniture, a Docker container can hold any application: a web server, a database, a custom program, along with all its necessary dependencies, libraries, and configurations. It's entirely self-sufficient. An application running inside a Docker container has its own isolated environment. It believes it has its own operating system, its own files, and its own network interfaces, even though it's sharing the core operating system kernel with many other containers on the same host machine. This isolation is key to solving the "it works on my machine" problem. If an application runs in its Docker container on one machine, It will run exactly the same way in the same Docker container on any other machine with Docker installed. Containers versus virtual machines, a key distinction. At this point, you might be thinking, this sounds a lot like virtual machines, VMS. While VMS also provide isolation and consistency, there's a fundamental difference. Virtual machines, VMS. Think of a VM as a complete, separate computer running within your computer. Each VM has its own full operating system, like Windows, Linux, or macOS, its own virtual hardware, CPU, RAM, hard disk, and a hypervisor, like VMware, VirtualBox, or Hyper-V to manage it. This means each VM is quite large, often several gigabytes, and takes time to boot up because it's starting an entire operating system from scratch. VMS provides strong isolation at the hardware level. Containers. In contrast, containers share the host machine's operating system kernel. They don't have their own separate operating system. Instead, they bundle only the application and its specific dependencies, utilizing OS-level virtualization features, like Linux namespaces and cgroups, to provide isolation. This makes containers incredibly lightweight, megabytes instead of gigabytes, start almost instantly, milliseconds, and consume fewer resources. They provide isolation at the process level. Analogy. If a virtual machine is like having a separate house for each application, complete with its own utilities, foundation, and roof, then a container is more like an apartment within a large, modern building. Each apartment container has its own distinct living space and furnishings, application and dependencies, but they all share the building's core infrastructure, the host OS kernel, like plumbing, electricity, and shared walls. This shared infrastructure makes them much more efficient and quicker to set up. Why Docker? The platform that democratized containers. The concept of containers has existed for many years, even before Docker. Technologies like CRUD in Unix, FreeBSD jails, and LXC Linux containers laid the groundwork. However, these tools were often complex, difficult to use, and lacked standardization. Docker, launched in 2013, changed everything. It didn't invent containers, but it made them accessible, user-friendly, and portable. Docker provided a simple command line interface, CLI, easy to build, run, and manage containers. A standard packaging format, Docker images, ensuring consistency across environments. Docker Hub, a central registry for sharing pre-built images, similar to an app store for software components. A robust ecosystem, tools for multi-container applications, Docker Compose, and complex orchestration Docker Swarm, and later, facilitating the rise of Kubernetes. Docker turned a niche technology into an industry standard. It became the platform that truly democratized containerization, making it a staple for individual developers, small startups, and massive enterprises alike. The microservices revolution. Beyond solving the works on my machine problem, containers, particularly with Docker, became a fundamental building block for a new architectural paradigm. Microservices. Instead of building one gigantic, monolithic application that handles everything, microservices architecture involves breaking down an application into a collection of small, independent services. Each service performs a single function, runs in its own process, and communicates with others via well-defined APIs. Containers are a perfect fit for microservices. Each microservice can be packaged into its own isolated Docker container, allowing teams to develop, deploy, and scale services independently. This leads to faster development cycles, easier maintenance, and improved resilience. If one small service fails, it doesn't bring down the entire application. Benefits of Docker summarized. To recap, adopting Docker brings a wealth of advantages. Consistency. Build once, run anywhere. What works in development will work identically in testing and production. Isolation. Applications and environments are encapsulated, preventing conflicts and ensuring predictable behavior. Portability. Containers can run on any machine, your laptop, a cloud server, a local data center that has Docker installed. Efficiency. Containers are lightweight, start quickly, and use fewer system resources than virtual machines. Speed. Faster development cycles due to simplified environment setup, rapid testing, and quicker deployments. Scalability. Easily scale applications up or down by launching or stopping container instances. Version control. Docker images can be easily versioned and rolled back, similar to code. What you'll learn in this book. This book is your comprehensive guide to understanding and mastering Docker. We'll start from the very beginning, assuming you have no prior knowledge of containers, and progressively build your expertise. You will learn how to install Docker on your operating system, understand the fundamental concepts of images and containers, run and manage your first containers, build your own custom images using Dockerfiles, manage data persistence and networking for your applications, orchestrate multi-container applications with Docker Compose, share your images with the world using Docker Hub, glimpse into advanced topics like container orchestration, Kubernetes, and best practices for security and efficiency. Learn to troubleshoot common Docker issues, explore real-world applications and the future of containers. By the end of this journey, you won't just understand Docker. You'll be able to confidently leverage its power to streamline your development workflow, simplify deployments, and banish the "it works on my machine" problem from your vocabulary forever. Let's embark on this containerized voyage. Chapter 2, Setting Sail, Installing Docker and Your First Container. In the previous chapter, we explored why Docker matters, understanding the fundamental problems it solves, and the transformative power of containerization. Now, it's time to get hands-on. This chapter will guide you through the process of installing Docker on your machine and running your very first container. Consider this your embarkation, setting the basic course for our containerized journey. Understanding the Docker ecosystem. Before we begin the installation, it's helpful to understand the core components of the Docker ecosystem you'll be interacting with. Docker Engine. This is the heart of Docker. It's a client-server application consisting of a Docker daemon, a persistent background process often referred to as Dockered on Linux, which manages all Docker objects like images, containers, networks, and volumes. Docker Client. This is how you interact with the Docker engine. Most commonly, it's the Docker command line interface, CLI tool. When you type Docker run or Docker ps into your terminal, the Docker client sends these commands to the Docker daemon, which then executes them. Docker Desktop. For Windows and Mac OS users, Docker Desktop provides an easy-to-install application that includes the Docker engine, Docker CLI client, Docker Compose, and other tools, all in one package, with a user-friendly graphical interface. Docker Hub. This is a public registry service, a vast online repository where you can find and share Docker images. Think of it as a central app store for Docker applications and components. So, when you issue a command like Docker run hello world, your Docker client sends that command to the Docker engine, which then performs the necessary actions, like downloading the hello world image from Docker Hub and running it as a container. Installation Guide. Getting Docker on your machine. The installation process varies slightly depending on your operating system. For the most up-to-date and specific instructions, always refer to the official Docker documentation, as installation steps can evolve. However, here's a general overview for common operating systems. For Windows users, Docker Desktop. If you're on Windows 10 Pro, Enterprise, or Education, version 1903 or higher, or Windows 11, Docker Desktop is the recommended path. It leverages Windows Subsystem for Linux, WSL2, which provides a full Linux kernel environment within Windows, allowing Docker to run natively and efficiently. Enable WSL2. You'll first need to ensure WSL2 is enabled on your system. This involves a few PowerShell commands and a kernel update package download. Detailed instructions are available on Microsoft's and Docker's websites. Download Docker Desktop. Visit the official Docker website and download the Docker Desktop installer for Windows. Run the installer, execute the downloaded exe file, and follow the on-screen prompts. Ensure the option Install required Windows components for WSL2 is checked during installation. Start Docker Desktop. Once installed, launch Docker Desktop. It will typically start in the background and display an icon in your system tray. A green Docker Desktop is running, status indicates success. For Mac OS users, Docker Desktop. Docker Desktop is also the recommended way to install Docker on macOS. It uses macOS built-in virtualization framework, Hyperkit, to run the Linux-based Docker engine seamlessly. Download Docker Desktop. Go to the official Docker website and download the Docker Desktop installer for macOS. Make sure to choose the correct chip architecture, Intel or Apple Silicon. Install Docker Desktop. Drag the application icon to your Applications folder. Launch Docker Desktop. Open the application. You might need to grant it necessary permissions for virtualization. A green Docker Desktop is running. Status in the menu bar indicates readiness. For Linux users, Docker Engine. On Linux distributions, you typically install the Docker engine directly. While Docker Desktop for Linux exists, most users prefer the lighter Docker engine approach, managed via command line. The process usually involves adding Docker's official repository to your system's package manager. For Ubuntu/Debian-based systems, a common choice, update package index. Open your terminal and update your package manager's index. Sudo apt update. Install prerequisites. Install necessary packages for HTTPS transport and Docker's GPG key. Sudo apt install certificates curl GNU-PG. Add Docker's official GPG key. Download and add Docker's official GPG key to your system. Add Docker repository. Set up the stable Docker repository. Install Docker Engine. Install Docker Engine, Containerized and Docker Compose. Sudo apt install dockerc dockerccli, container.io Docker builds plugin Docker Compose plugin. Add user to Docker group, optional but recommended. To run Docker commands without sudo, add your user to the Docker group. Sudo usermod ag Docker user. You'll need to log out and log back in or reboot for this change to take effect. For other Linux distributions, Fedora, CentOS, Arch Linux, the specific commands will differ, so always consult the Docker documentation for your distribution. Verify your installation. Once you believe Docker is installed, open your terminal or command prompt and run these commands. To check the Docker version. To get detailed information about your Docker installation. Docker info. If these commands return version information and system details without errors, congratulations. Docker is successfully installed and running on your machine. Your first container. The classic Hello World. Now that Docker is installed, let's run our very first container. It's customary in programming to start with a Hello World example, and Docker is no different. This seemingly simple command will demonstrate the core Docker workflow. Open your terminal or command prompt and type Docker run Hello World. Press enter. What just happened? Let's break down the magic. Docker run. This is the primary command for running a container. Hello World. This is the name of the image we want to run. An image is a lightweight, standalone, executable package of software that includes everything needed to run an application: code, runtime, system tools, system libraries, and settings. When you executed the command, Docker performed several steps. Check local cache. First, the Docker client looked for a local copy of the Hello World image on your machine. Pull image from Docker Hub. Since it's likely your first time running this, Docker didn't find the image locally. So, it automatically connected to Docker Hub, the default public registry, and downloaded the Hello World image. You would have seen messages indicating the download progress. Create a container. Once the image was downloaded, Docker used it as a blueprint to create a new, isolated container instance. Run the container. Docker then started this container. The Hello World program inside the container executed, printing a message to your terminal similar to Hello from Docker. This message shows that your installation appears to be working correctly. Additional diagnostic messages. Exit the container. After printing its message, the Hello World program finished its task and exited, and so did the container. This simple example illustrates Docker's power of portability. The Hello World image contains everything it needs to run, ensuring it executes identically on any machine with Docker, regardless of the underlying operating system or configuration. Running a more useful container. A simple web server. Let's try something a bit more interactive. We'll run a popular web server, Nginx, inside a Docker container. In your terminal, type Docker run p808080 Nginx. and then press Enter. This command is slightly more complex, but immensely practical. Docker run nginx. Similar to Hello World, this tells Docker to run a container from the nginx image. If you don't have it locally, Docker will pull it from Docker Hub. P808080. This is the crucial part that enables you to access the web server. It establishes a port mapping, or port publishing. The 80 after the colon refers to the port inside the container where the nginx web server is listening. Web servers commonly listen on port 80 for HTTP traffic. The 8080 before the colon refers to the port on your host machine, your laptop or desktop, that Docker maps to the container's port 80. After running this command, you'll see some output confirming nginx has started within the container. Now, open your web browser and navigate to http localhost :8080. You should see the default Welcome to Nginx page. Congratulations, you are now serving a web page from an application running inside a Docker container. To stop this container, go back to your terminal where the nginx logs are scrolling and press Ctrl+C. Basic container management, your fleet control panel. Running containers is just the beginning. You'll also need to manage them. Here are some fundamental commands to help you keep track of and control your containers. Docker ps process status. This command lists all currently running containers on your system. It will show you information like the container ID, the image it's based on, the command it's running when it was created, its status, exposed ports, and an automatically generated name. Try running Docker ps after starting the nginx container, but before pressing Ctrl+C. You'll see it listed. After Ctrl+C, it will disappear from this list. Docker ps all processes status. This command lists all containers, both running and those that have stopped or exited. This is useful for seeing containers that have finished their job, like Hello World, or those you stopped manually. Go ahead and run Docker ps now. You should see both your Hello World container in an exited state and possibly the nginx container also exited if you pressed Ctrl+C. Docker stop container name. This command gracefully stops a running container. Docker will send a SIGTERM signal, a shutdown request, to the container's main process, allowing it to shut down cleanly. If the container doesn't stop within a given timeout, usually 10 seconds, Docker will force stop it. When you run a container without specifying its name, Docker assigns a random one like Hungerlemen or Festivehopper. You can find this name or the container ID using Docker ps. For example, if nginx was still running in a detached mode, which we'll explore later, and its name was unrivaledbooth, you'd type Docker stop unrivaledbooth. Docker start container name. This command starts a stopped container. If you stopped your nginx container, you could restart it using this command. Docker rm container name. This command removes a stopped container. Once a container is removed, all its writable layers, that is, any changes made within the container since it started, are gone. You cannot start a removed container. To clean up, you might run Docker rm ID of Hello World container, ID of nginx container. Replace with actual IDs or names from Docker PSA. Or even Docker rm, Docker PSAC, to remove all stopped containers. Use this with caution if you have important stopped containers. By using Docker run, Docker ps, Docker stop, and Docker rm, you already have the foundational tools to take control of individual containers. This covers the most common day-to-day operations. Key takeaways. You've successfully installed Docker on your system, run your first 2 containers, and taken your first steps in managing them from the command line. You can now understand the basic client-server architecture of Docker. Get Docker running on your Windows, Mac OS, or Linux machine. Run an application like Hello World or nginx in an isolated container environment. Monitor running containers and clean up exited ones. In the next chapter, we'll delve deeper into the core concepts introduced here: Docker images and Docker containers. We'll explore their anatomy, how they differ, and how Docker manages their lifecycle, giving you a clearer picture of the ship's components and what they truly do. Chapter 3, Understanding the Ship: Images, Containers, and What They Do. In the previous chapter, you successfully installed Docker and ran your first few containers. You issued commands like docker run hello world and docker run p808080 nginx. These commands implicitly reference two fundamental concepts, Docker images and Docker containers. While they might seem similar, understanding their distinct roles is crucial to mastering Docker. Think of it this way. To build a ship, you first need a detailed blueprint. Once you have the blueprint, you can build many identical ships from that single plan. In the world of Docker, the blueprint is the Docker image. The actual running ship is the Docker container. Let's explore these two core components in detail. Docker images, the blueprints of your applications. A Docker image is a read-only template that contains all the necessary components to run an application. This includes the application's code, a runtime like Node.js or Python, system tools, libraries, and dependencies, all encapsulated in a neat, portable package. When you executed docker run nginx, if you didn't have the nginx image locally, Docker went to Docker Hub and pulled it down. This image then served as the blueprint to create and run your nginx container. The concept of layers, efficiency in action. One of the most powerful and efficient aspects of Docker images is their layered architecture. An image isn't a single, monolithic file. It's composed of multiple read-only layers stacked on top of each other. Each layer represents a specific instruction in the Dockerfile, which we'll explore in the next chapter, that built the image. For example, an nginx image might have layers for the base operating system, e.g., Alpine Linux, installing nginx, adding default configuration files. When you build a new image, Docker reuses existing layers from its cache. If you make a small change, only the affected layer and subsequent layers need to be rebuilt, not the entire image. This significantly speeds up image building, makes images smaller, and minimizes disk usage because multiple images can share common base layers. Image naming and tagging. Docker images are identified by a name and often a tag. The tag typically denotes a version or specific variant of the image. Nginx latest refers to the most recent official Nginx image. Latest is a common default tag if none is specified for an image. Ubuntu 0.04. A specific version of the Ubuntu operating system image. My custom app v1.0, a user-defined image name and version. You can often pull an image simply by its name, like docker pull Ubuntu, and Docker will default to the latest tag. Managing your local images. You can view the images stored on your local machine using a few simple commands. Docker images or Docker image ls lists all images currently downloaded on your system. Docker images, repository tag image ID created size. Nginx latest C2, 7078351651 weeks ago 142 MB. Hello world latest Feb 5D9, Fe6A5 3 months ago 13.3 KB. Ubuntu 20.04B93C9, dabbed 1E3 weeks ago 77.8 MB. You'll notice image ID, a unique identifier, created date and size. Note how relatively small they are due to layering and efficiency. Docker pull image name, tag, explicitly downloads an image from a registry, like Docker Hub, to your local machine. Docker pull Ubuntu 20.04. 20.04, pulling from library Ubuntu. Download progress. Status, downloaded newer image for Ubuntu 20.04. Docker.io/library/Ubuntu 20.04. Docker RMI image name tag, or imaged, removes an image from your local system. You must stop and remove any containers using that image before you can remove the image itself. Docker RMI hello world. Untagged hello world latest. Deleted. SHA-256, Feb 5D9 Fe6A5. Docker containers, live instances of your blueprints. A Docker container is a runnable instance of a Docker image. When you run an image, Docker creates a container from it. While the image is read-only, the container adds a thin, writable layer on top of the image's layers. This writable layer is where all changes unique to that container, e.g., new files, modifications to existing files, process logs, are stored. This writable layer is crucial for several reasons. Isolation. Each container gets its own writable layer, ensuring that changes in one container do not affect the base image or other containers running from the same image. Ephemeral nature. By default, when a container is removed, its writable layer is also discarded. This means any data written inside the container that isn't explicitly saved to a permanent volume, which we'll cover in Chapter 5, is lost. This ephemeral nature promotes stateless applications and easy recreation. Container isolation. How it works. Docker achieves its powerful isolation through a combination of Linux kernel features. Though Docker Desktop on Windows Mac OS uses a light VM to run a Linux kernel first. Namespaces provide isolation for various system resources. Each container gets its own isolated view of process IDs, PID namespace. Processes inside a container think they are PID1. Network net namespace. Each container has its own network interfaces, IP addresses, and routing tables. Mounts MNT namespace. Each container has its own view of the file system. Users user namespace. User IDs can be mapped from host to container, offering security benefits. Control groups, C groups, limit and account for resource usage, CPU, memory, disk I/O, network for a group of processes. This prevents one container from hogging all system resources and impacting others. This combination allows containers to feel like separate, lightweight virtual machines while sharing the underlying host kernel, leading to their efficiency and speed. Container lifecycle in detail. A Docker container proceeds through various stages in its life. Understanding these states helps you manage your applications effectively. Created. You've issued a Docker create command, but the container hasn't started yet. It exists but isn't running. Running, the container is actively executing its command. Paused, the container's processes have been temporarily suspended. Exited. The container's main process has finished, either successfully or with an error. It's no longer running but still exists on your system. Dead. A container that has been stopped and marked for removal, possibly due to a critical error not handled by the Docker daemon. Here are the commands to control a container's lifecycle. Docker create image name creates a new container from an image but doesn't start it. You then use Docker start to get it running. Docker run is essentially Docker create followed by Docker start. Docker start container reader name starts one or more stopped containers. Docker start myengine x container. Myengine x container. Docker stop container reader name gracefully stops a running container. It sends a SIGTERM signal, allowing the application inside to shut down cleanly. If the container doesn't respond within a timeout, default 10 seconds, Docker sends a SIGKILL to force termination. Docker stop myengine x container. Myengine x container. Docker kill container reader name forcefully stops a running container by sending a SIGKILL signal. Use this when Docker stop doesn't work, but be aware that the container might not clean up resources properly. Docker pause container reader name suspends all processes in a container. It essentially freezes the container's state. Docker unpause container reader name unpauses a paused container. Docker restart container reader name stops and then starts a container. Useful for applying configuration changes or simply resetting a container. Docker rm container reader name removes one or more stopped containers. Once removed, all data in its writable layer is lost. Docker rm myengine x container. Myengine x container. You can't remove a running container unless you use the force flag, which will implicitly stop it first. Interacting with running containers. Once a container is running, how do you see what's happening inside or make changes? Docker PS, as seen before, lists running containers. Add no trunk to see full IDs and names. Add L or latest to show the last created container. Add format for custom output, e.g., Docker PS format, ID \T, names \T, status. Docker logs container reader name displays the standard output and standard error streams generated by the container's main process. This is your primary way to see application logs. Docker logs myengine x container. Docker rentrepoint.sh. Configuration complete, ready for startup. 172.17.0.1, 21/Jul/2023 1030, 45 + 0000. get/http 1.1 200/612 Mozilla/5.0. Add F or follow to stream logs in real time, like tail F. Docker execute container name command runs a new command inside a running container. This is incredibly powerful for debugging or performing administrative tasks. I and T are standard flags for interactive sessions. I keeps stdin open, and T allocates a sudo tty, letting you use a shell. A common use is to get a bash shell inside a container. Docker exec it myengine x container bash, or sh if bash isn't installed. Once inside, you can navigate the file system, run commands, and inspect the container's environment. Type exit to leave the container's shell. Docker inspect container name or image ID provides a detailed, low-level JSON output of a Docker object container, image, volume, network. This includes IP addresses, mounted volumes, configuration settings, and much more. Essential for deep debugging. Docker inspect myengine x container more. Pipe to more or less for easier reading of large JSON output. Analogy revisited, blueprint versus cake. To solidify the image container distinction, let's refine our analogy. Imagine a blueprint for a cake. It lists ingredients, measurements, baking time, and decorating instructions. This blueprint is like a Docker image, a fixed, unchangeable set of instructions and components. When you follow that blueprint and bake a cake, you've created an instance of that blueprint. Each cake could be slightly different in its frosting design, but it's still fundamentally the same cake. This baked cake is like a Docker container, a running, active instance of the image. You can have many cakes containers from one blueprint image. If you eat the cake, it's gone, container removed, but you still have the blueprint to bake another one. Key takeaways. By now, you should have a firm grasp of the fundamental building blocks of Docker. Docker images are read-only templates, essentially blueprints of your applications, composed of layers for efficiency. Docker containers are live, isolated, runnable instances of those images, with a thin, writable layer for changes. You can effectively manage the lifecycle of your containers, create, start, stop, remove, and interact with them, view logs, execute commands inside, using the Docker CLI. This understanding is the foundation upon which all further Docker knowledge is built. In the next chapter, we'll move from simply running pre-built images to crafting your very own custom images using a powerful tool called the Dockerfile. Get ready to build your own fleet. Chapter 4, Building Your Fleet, Crafting Custom Images with Dockerfiles. So far, we've focused on running pre-built Docker images, like Hello World and Nginx, directly from Docker Hub. This is a powerful starting point, but what happens when you want to containerize your own applications? Your specialized web server, your custom database, or your unique data processing script. That's where building custom images comes in, and the primary tool for this is the Dockerfile. Think of a Dockerfile as a recipe. It's a text file filled with instructions that Docker reads to understand how to assemble your custom image layer by layer. Every instruction in a Dockerfile creates a new, read-only layer in the image, adhering to the layered architecture we discussed in Chapter 3. The need for custom images. While Docker Hub offers a vast array of ready-to-use images, your applications likely have specific requirements. Specific application code. You need your own source code to be part of the image. Unique dependencies. Your application might require specific versions of libraries, compilers, or operating system packages not found in generic base images. Custom configurations. You might have specific network settings, environment variables, or startup commands. The Dockerfile allows you to define all these requirements precisely, ensuring your application runs consistently across different environments. Introducing the Dockerfile. A Dockerfile is a plain text file, conventionally named Dockerfile, without any file extension. Inside it, you list instructions, one per line, that Docker executes sequentially to build your image. Let's look at a simple example before dissecting each instruction. Imagine you have a basic Python script, appy, that simply prints hello from my Python app. Your project directory might look like this: my Python app, appy, Dockerfile, appy print, hello from my Python app. Dockerfile, use an official Python runtime as a parent image. From Python, 3.9 Slim Buster. Set the working directory in the container. WRKDIR app. Copy the current directory, contents into the container at app. Copy, app. Run the command when the container starts. cmd python appy. To build an image from this Dockerfile, you would navigate to the MyPython app directory in your terminal and run docker build tmypython app 1.0. Let's break down this command. Docker build, the command to initiate an image build. tmypython app 1.0. This tags your image, giving it a name MyPython app and a version 1.0. Tags are crucial for identifying and managing your images. If you omit the tag, Docker defaults to latest. The dot. This specifies the build context. The build context is the set of files and directories at the specified path. In this case, the current directory that Docker can access during the build process. When Docker builds an image, it sends this entire context to the Docker daemon. Once the build is complete, you can run your custom image. Docker run MyPython app 1.0. You should see Hello from MyPython app printed to your console. You built your first custom image. Essential Dockerfile instructions. Now let's look at the most common Dockerfile instructions in detail. From image, tag, purpose, specifies the base image for your build. Every Dockerfile must start with a from instruction. This layer typically provides the operating system environment, e.g., Ubuntu, Alpine Linux, and often a language runtime, e.g., Python, Node. Best practice. Choose a minimal base image, like Alpine or Slim versions, to keep your final image size small and improve security by reducing the attack surface. Example: from Ubuntu, 20.04 from Node, 18 Slim from Scratch for building smallest possible images, often for Go binaries. WORKDIR path. Purpose. Sets the working directory for any run, cmd, entrypoint, copy, or add instruction that follows it in the Dockerfile. It makes navigating within the container's file system much easier. Best practice. Define a clear working directory, often app/usr/src/app, or similar, to organize your application files inside the container. Example: WRKDIR app. Copy source destination, purpose. Copies files and directories from the build context, your host machine, into the container's file system. Examples: copy. App copies everything from the current build context, stands for the current directory on your host, into the app directory inside the container. Copy appy app/appy copies a specific file. Copy HTML usr/share/nginx/html copies a local HTML directory to the nginx web root. Compared to ADD. While ADD can also copy files, it has extra features like extracting tar archives and fetching remote URLs. Copy is generally preferred for simple file copying as it's more transparent and explicit. Use add only if you need those extra features. Run command, purpose, executes commands during the image build process. This is where you install software, update packages, compile code, or set up the environment required for your application. Each run instruction creates a new layer. Example: run apt-get update and an apt-get install ymypackage installs a package. Run pip install r requirements.txt installs Python dependencies. Run make install compiles and installs software from source. Expose port, purpose. Informs Docker that the container listens on the specified network ports at runtime. It acts as documentation, but does not actually publish the port. Publishing is done with the P flag during Docker run. Best practice. Explicitly expose all ports your service uses. Example: expose 80.443, expose 3000. CMD executable, param1, param2. Purpose provides default arguments for executing a container. There can only be one CMD instruction in a Dockerfile. If you specify multiple CMD instructions, only the last one will take effect. Behavior. If you run the container without specifying a command, e.g., docker run my image, the CMD instructions command is executed. If you do specify a command, e.g., docker run my image lslaw, the CMD instruction is ignored, and your specified command is executed instead. Format. Use the exec form with square brackets and double quotes, as shown in the example. It's generally preferred because Docker executes the command directly without involving a shell. The shell form, cmd command param1 param2, executes the command via /bin/shc, which can have subtle differences in signal handling. Example: cmd python, appy, cmd nginx, g daemon off. entrypoint executable, param1, param2, purpose, configures a container to run as an executable. It defines the main command that always runs when the container starts. Behavior: unlike cmd, the entrypoint instruction is not ignored when you specify a command during Docker run. Instead, the command you provide at runtime is appended as arguments to the entrypoint command. This makes entrypoint ideal for creating utility containers, e.g., Docker run mydb client show tables, or wrapper scripts that do some setup before executing the main application. Example combined with cmd. entrypoint /usr/src/app/entry.sh. cmd start server. If you run Docker run myapp, it executes usr/src/app/entry.sh start server. If you run Docker run myapp runtists, it executes usr/src/app/entry.sh runtists. Hands-on example: containerizing a simple Node.js web application. Let's put what we've learned into practice by containerizing a basic Node.js web server. Create a new directory called Node Docker App. Inside it, create two files, package.json and app.js. Package.json. Name Node Docker App. Version 1.0.0. Description: a simple Node.js web server. Main app.js. Script: start Node app.js. Dependencies: Express 4.17.1. App.js, const express equals require express. Const app equals express. Const port equals 3000. App-get / rec raise equals. Res send hello from Node.js in a Docker container. App listen port equals. Console log app listening at HTTP localhost $port. Now create the Docker file in the same directory, Dockerfile. Use an official Node.js runtime as a parent image. From Node 18 Alpine. Set the working directory in the container wrkdir/usr/src/app. Copy package.json and package.lock.json first to leverage Docker's layer caching. This ensures npm install runs only if these files chain. Copy package.json. Install application dependencies. Run npm install. Copy the rest of the application source code. Copy. Expose the port the app runs on. Expose 3000. Define the command to run the application. cmd npm start. Now open your terminal, navigate to the Node Docker App directory, and build the image. Docker build tnode web app 1.0. You'll see Docker executing each instruction, downloading the base image, installing dependencies, and copying your files. If the build is successful, you'll see a message like successfully tagged Node Web App 1.0. Finally, run your container. Docker run p80803000 Node Web App 1.0. Open your web browser and go to http localhost:8080/. You should see hello from Node.js in a Docker container. In your browser, you've just containerized a Node.js application. Dockerfile best practices for efficiency and security. Building effective Docker images isn't just about getting them to work. It's about making them efficient, small, and secure. Leverage Docker's layer caching. Docker caches each layer during the build process. If an instruction and its context hasn't changed, Docker will reuse the cached layer, speeding up subsequent builds. Order matters. Place instructions that change least often, like from, run for installing OS packages, at the top. Place instructions that change frequently, like copy for application code later. In our Node.js example, we copied package.json before the main application code and npm install. If only the app.js changes, Docker will reuse the npm install layer, avoiding a lengthy reinstallation of dependencies. Minimize image size. Choose a minimal base image. Alpine or slim versions of official images are much smaller than full Linux distributions. Combine run instructions. Each run creates a new layer. Combining multiple commands with and reduces the number of layers. For example, Run apt-get update and an apt-get install why no install recommends my package, and an rm ref var /lib /apt /lists / the rm part cleans up build cache. Remove build dependencies. Don't include build tools or development libraries in your final image unless absolutely necessary for runtime. Multi-stage builds. This is a crucial technique for creating small, production-ready images by separating the build environment from the runtime environment. How it works: you use multiple from instructions in a single Docker file. An early stage might include compilers, SDKs, and build tools. A later stage copies only the compiled artifacts from the previous stage into a much smaller base image. Example, compiling a Go application. Stage 1, build the application. From Galing, 1.20 Alpine as builder. WRKDIR app. Copy, run go build omyapp. Stage 2. Create the final lean image. From Alpine, latest. WRKDIR app. Copy from equals builder /app /myapp. cmd/myapp. This build is much smaller than one that includes the entire Go SDK. Use Docker ignore. Similar to git ignore, a Docker ignore file specifies files and directories that should be excluded from the build context. Benefit: prevents unnecessary files like node modules on your host, git histories, temp files from being sent to the Docker daemon, significantly speeding up build times and preventing unwanted files from ending up in your image. Run as a non-root user. By default, processes inside a container run as root. This is a security risk. If an attacker gains control of your container, they would have root privileges inside. Use the user instruction to switch to a non-root user after necessary root-level operations, like installing packages. Run a deucer system, no create home user. User muser. We'll delve more into security practices in Chapter 9. Key takeaways. You've now learned how to craft your own Docker images, moving beyond simply using pre-built ones. You understand the purpose and basic structure of a Docker file. The essential Docker file instructions from WRKDIR, copy, run, expose, CMD, ENTRYPOINT, and their distinct roles. How to build a custom image and run a container from it. Crucial best practices like layer caching, minimizing image size, and using multi-stage builds. With this knowledge, you are no longer just a passenger on the Docker ship. You're actively building new parts of its fleet. In the next chapter, we'll address another critical aspect of containerization: how to handle data that needs to persist beyond the life of a container and how containers communicate with each other and the outside world through networking. Chapter 5, Persistent Storage and Networking, your container's memory and communication. In the previous chapters, you've learned to run pre-built and custom Docker containers. You've seen how they instantly spin up, perform their task, and then, if not explicitly kept alive, exit. This ephemeral nature is a core principle of containers. They're designed to be transient, easily started and stopped, recreated, or even destroyed. However, real-world applications aren't quite so fleeting. Databases need to store data permanently. Web applications often allow users to upload files. Logging systems need to record events over time. If a container storing this critical data is simply removed, all that information would be lost. This brings us to our first major topic: data persistence. The second critical challenge arises when applications aren't just single, isolated units. Most modern applications consist of multiple services: a web server, an application backend, a database, perhaps a caching layer. These services need to communicate with each other and with the outside world. This introduces the world of Docker networking. Together, persistent storage and networking transform containers from isolated, disposable units into robust building blocks for complex, stateful, and interconnected software systems. Persistent storage, your container's memory. Imagine you have a notepad inside your ship. You write down important coordinates. If that ship were to suddenly sink, your notes would be gone. To keep those coordinates safe, you'd transfer them to a sturdy, waterproof logbook that exists independently of the ship. This is the essence of data persistence with Docker. By default, any data written inside a container's writable layer, refer back to Chapter 3, is tied to that specific container instance. If you remove the container, that data vanishes. For applications that handle important, long-lived data, this ephemerality is unacceptable. Docker provides two primary mechanisms to persist data generated or used by Docker containers: volumes and bind mounts. 1. Docker volumes, the preferred way. Docker volumes are the standard and recommended way to persist data in Docker. They are fully managed by Docker. When you create a volume, Docker handles the actual creation and management of the storage on the host machine, typically located in a special directory. For example, /var/lib/docker/volumes/ on Linux, though you shouldn't directly interact with these folders. Volumes are designed to be explicitly created and removed and can be easily backed up or migrated. How they work: you tell Docker to create a named volume, and then you mount this volume into a specific path inside your container. Any data written to that path inside the container will actually be written to the Docker-managed volume on the host, persisting even if the container is stopped, removed, or replaced. Creating and managing volumes. Create a named volume. Docker volume create my data. List volumes. Docker volume ls. Inspect a volume. Docker volume inspect my data shows its mount point on the host. Remove a volume. Docker volume rm my data. Make sure no containers are using it. Using a named volume with a container. You attach a named volume to a container using the v or volume flag with the format volume name, /path/ and /container. Hands-on example: running a database with a named volume. Let's run a PostgreSQL database container and ensure its data persists. Without a volume, if you remove the container, your database contents would be lost. Create a volume for your database data. Docker volume create pg data. Run a PostgreSQL container, attaching the volume. Docker run name some Postgres postgres password equals my secret password, p54325432 vpg data, /var/lib/postgresql/data dpostgres. Name some Postgres. Assigns a readable name to the container. Postgres password equals my secret password. Sets an environment variable required by the Postgres image. p54325432. Maps the container's PostgreSQL port 5432 to your host's port 5432. VPG data, /var/lib/postgresql/data. This is the key. It mounts the PG data named volume to the /var/lib/postgresql/data directory inside the container, which is where PostgreSQL stores its data. Dpostgres runs the Postgres image in detached mode in the background. Now, even if you stop and remove the some Postgres container, Docker stop some Postgres, and in Docker rm some Postgres, the PG data volume and your database data will remain safe. You can then run a new PostgreSQL container and simply attach the same PG data volume, and your database will pick up exactly where it left off. 2. Bind mounts. Explicit host control. Bind mounts allow you to mount a file or directory from the host machine's file system directly into a container. Unlike volumes, Docker doesn't manage their location on the host. You explicitly specify the host path. How they work: you tell Docker the exact path on your host and the exact path inside the container where you want them connected. Whatever exists or is written at that path on the host will appear inside the container. Using a bind mount with a container, you use the same v or volume flag, but with the format host path, /path/ and /container. Hands-on example: development with live code reloading using bind mounts. Bind mounts are incredibly useful for development workflows, especially with technologies that support hot reloading or live updates. If you modify your code on your host machine, the changes are immediately reflected inside the running container, without needing to rebuild the image or restart the container. Let's use our Node.js example from Chapter 4. Ensure your Node Docker app directory contains app.js, package.json, and Dockerfile. Run the Node.js app with a bind mount. Docker run name dev node app p80803000v pwd /usr/src/app dnode web app 1.0 pwd /usr/src/app. This mounts your current working directory. pwd on Linux Mac OS. Use %cd% on Windows CMD or a full path like C. /users/your user/node Docker app on Windows PowerShell CMD to the /usr/src/app directory inside the container. This means the app.js and package.json files inside the container are now linked directly to your host's files. Verify it's running. Open http localhost:8080 in your browser. You should see hello from Node.js in a Docker container. Make a change and observe. Keep the container running. Go back to your app.js file on your host machine and change the message. Send hello from Node.js with live updates. Changed line. Save the file. If your Node.js application is set up to watch for file changes, as many development servers are, you'll likely see the container's logs update, and reloading your browser at http localhost:8080 should reflect the new message instantly. Volumes versus bind mounts. When to use which? Feature use case named volumes bind mounts. Data persistence yes, fully managed by Docker. Yes, maps directly to host file system. Management Docker manages location, easy to create delete. You manage location on host, Docker just connects it. Portability more portable. Works across various OSes less portable. Host path is OS specific. Common use cases database data, persistent queues, cached data. Development, live coding, injecting configuration files. Performance generally perform better, especially for I/O. Can have performance overhead, particularly on Docker desktop, Windows Mac OS, due to virtualization overhead. Security more secure. Container cannot access arbitrary host files. Less secure. Container could access sensitive host files outside the bind mount if misconfigured. For most application data persistence, named volumes are preferred. Bind mounts are excellent for development where you want direct host access to files or for situations where you explicitly control host-specific configurations. Networking, your container's communication. Containers need to talk. They need to talk to each other, e.g., a web server talks to a database, and they need to talk to the outside world, e.g., your browser talks to a web server. Docker handles this with its flexible networking capabilities. Network drivers, the foundation. Docker uses different network drivers to provide various types of network connectivity for containers. The most common is the bridge driver. The default bridge network. When you install Docker, it creates a default bridge network, cleverly named bridge. Unless you specify otherwise, all containers you run are automatically connected to this bridge network. Internal IP addresses. Each container connected to a bridge network gets its own internal IP address. Isolation from host. Containers by default are isolated from the host's network. They can communicate with other containers on the same bridge network using their internal IP addresses, but they cannot be reached directly from the host or external networks unless you specifically expose their ports. Port mapping P or publish, the gateway to the host. You've already used this in Chapter 2. The P host port, container port option when running a container creates a network route, often called a port forward or port publish, from your host machine to the container. Analogy, imagine your apartment container has a phone extension, port 80. You want people outside the building, host, to call your extension. You ask the building manager, Docker, to forward calls from the building's main number, host port 8080, directly to your extension. Anyone calling 8080 on the building's outside line will reach your apartment's extension 80. Custom bridge networks for multi-container applications. While the default bridge network works, it has limitations, especially for multi-container applications. No automatic name resolution. Containers on the default bridge can't find each other by name, e.g., web app can't automatically find database. You'd have to use their dynamically assigned IP addresses, which change. Less isolation. All containers you run by default end up on the same bridge network, which isn't ideal for security or organization. Custom bridge networks solve these problems. When you create a custom bridge network, Docker provides automatic name resolution, DNS, allowing containers on that network to communicate with each other simply by their container name or service name. Hands-on example. Web app and database communication. Let's imagine you have a simple web application that needs to talk to a database. We'll put them on their own isolated network. Create a custom bridge network. Docker network create myapp network. Run the PostgreSQL container on this network. Docker run name myappdb network myapp network. Postgres password equals mysecret password v myapp data /var/lib/postgresql/data dpostgres. Network myapp network connects this container to your newly created network. Notice we don't publish port 5432 to the host because only the web app needs to talk to the database. Run the Node.js web app container on the same network. We need to modify our app.js slightly to connect to the database. For simplicity, we'll imagine it's an API server connecting to the database. Assume your app.js now makes a database connection to a host called myappdb, the container name we assigned. Let's use Nginx and assume it serves static content from a backend that uses the database. Docker run name myappweb network myapp network p8080d Nginx. Name myappweb, name for your web server. Network myapp network connects it to the same network as the database, p8080. Publishes the web server's port 80 to your host's port 80 so you can access it. Now, your myappweb container can reach myappdb simply by using myappdb as the hostname. Docker's DNS service on the myapp network resolves myappdb to the database container's internal IP address. This is a robust and scalable way for services to discover each other. Clean up the network. Docker stop myappweb myappdb. Docker rm myappweb myappdb. Docker network rm myapp network. Docker volume rm myapp data hash, if you created one for the DB dem. Other network drivers, briefly. While bridge networks, default and custom, cover most common local development and single-host production use cases, Docker offers other drivers for specialized needs. Host removes network isolation between the container and the host. The container directly uses the host's network stack. This can be faster, but sacrifices isolation. None provides no network interfaces for the container. Useful for containers that perform batch jobs and don't require network connectivity. Overlay. Used for multi-host networking, allowing containers on different Docker hosts to communicate as if they were on the same local network. This is crucial for Docker Swarm, Docker's built-in orchestration tool, and conceptually similar to how Kubernetes handles networking across a cluster. We'll touch on orchestration in Chapter 8. Key takeaways. Persistent storage and networking are indispensable for building any non-trivial application with Docker. You now understand the ephemeral nature of containers and why data persistence is crucial. How to use Docker volumes for managed, persistent storage, especially for databases and critical application data. How to use bind mounts for direct host file system access, primarily useful in development or for injecting configurations. The role of Docker networks, particularly the bridge driver. How custom bridge networks enable isolated and name-resolvable communication between multiple containers. The importance of port mapping, P, to expose container services to the host. You've learned to manage individual containers and define their storage and communication. However, managing multiple interdependent containers manually, with many Docker run commands, quickly becomes cumbersome. In the next chapter, we'll discover Docker Compose, a powerful tool that allows you to define and manage multi-container applications as a single, cohesive unit using a simple YAML file. Chapter 6, Orchestrating Your Armada, Managing Multi-Container Applications with Docker Compose. By now, you've mastered the art of running individual Docker containers, understood the nuances of images and volumes, and even connected them with custom networks. That's a strong foundation. However, most real-world applications aren't just one container. They're typically a collection of interconnected services, a web server, an application backend, a database, perhaps a caching layer, and more. Imagine trying to manage all these independently. You'd need to run the database container first, perhaps attach a volume. Run the backend container, making sure it can connect to the database, and configuring its connection string. Run the web server, mapping its ports. Ensure all are on the correct network. Remember all the Docker run flags for each. Stop them all, then start them all back up in the correct order after a change. This can quickly become a tangled mess, especially as your application grows or if you need to share your setup with team members. This is where Docker Compose sails in to save the day. The challenge of multi-container management. Let's illustrate the problem with a common application stack. A web application, e.g., our Node.js app from Chapter 4. A database, e.g., PostgreSQL from Chapter 5. Manually, you would create a volume for PG data. Potentially create a network. Docker network create my app network. Run the database. Docker run name mydb network myapp network postgres password equals secret vpg data /var/lib/postgresql/data dpostgres. Run the web app. Docker run name my web app network myapp network p80803000d your node app image. To shut them down, Docker stop my web app mydb, then Docker rm my web app mydb. To remove everything, Docker volume rm pg data, Docker network rm my app network. This is a lot of typing and a lot to remember. It's error-prone and tedious. Introducing Docker Compose, a single file for your stack. Docker Compose is a tool for defining and running multi-container Docker applications. With Compose, you use a YAML file, by default, Docker Compose YAML, to configure your application services. Then, with a single command, you can create and start all the services from your configuration. The advantages of Docker Compose are immediate. Single configuration point. All your services, networks, and volumes are defined in one easy-to-read file. Simplified lifecycle management. Start, stop, rebuild, and remove an entire application stack with single commands. Portability. Share your Docker Compose YAML file, and anyone with Docker and Docker Compose installed can spin up your entire development environment exactly as you defined it. Automatic networking and service discovery. Compose sets up a default network for your services, and they can automatically discover each other by their service names. Anatomy of Docker Compose YAML. The Docker Compose YAML file describes the services that make up your application. A typical Compose file has 3 top-level keys: services, volumes, and networks. Let's look at the structure for our web app and database example. Version 3.8 hash specifies the Compose file format version. Services web hash the name of our first service, the Node.js app. Build hash tell Compose to build the image from the Docker file in the current directory. Ports 80803000 hash host port, container port. Environment hash environment variables for the service. nodnv development database URL postgres / user password at db 5432 / mydatabase hash connect to the db service. Depenson hash ensures db service starts before web service. db volumes hash optional mount local code for development as in chapter 5 /usr/src/app. db hash the name of our second service, the PostgreSQL database. Image postgres 13 hash use a specific PostgreSQL image from Docker Hub. Environment postgresdb my database postgresuser user postgresbsswrd password. Volumes db data /var/lib/postgresql/data hash mount a named volume for data persistence. Volumes hash define the named volumes used by services. db data networks hash define custom networks, though Compose creates a default one if omitted. Default hash this is the bridge network automatically created for the services. Hash you can add specific configurations here if needed. Hash for example external. True if you want to use an existing network. Let's break down the key components. Version 3.8 declares the Compose file format version. Newer versions offer more features. 3.8 is a common, stable choice. Services, this section defines the individual components of your application. Each key under services becomes a separate container or multiple containers if scaled. Web/db. These are the arbitrary names you give to your services. These names are crucial because they become host names that services can use to communicate with each other within the Compose network. E.g., the web service can connect to the DB service using the hostname DB. Build instead of image, build tells Compose to build an image from a Docker file. The indicates that the Docker file is in the current directory. You can also specify context and Dockerfile for more complex builds. Image. Postgres 13 specifies a pre-existing Docker image to use from Docker Hub by default. Ports. Maps container ports to host ports, just like the P flag in Docker run. Environment. Sets environment variables inside the container, just like the E flag. Depenson declares dependencies between services. Compose will start DB before web. Important note. Depenson only ensures the container is started, not that the application inside the container is ready. For robust health checks, you typically add health check configurations or introduce retry logic in your application. Volumes under a service. Mounts volumes or bind mounts into the service container, similar to the V flag. Volumes, top level, defines named volumes that can be used by services. This is where DB data is declared. Networks, top level, defines custom networks to create. If omitted, Compose creates a default network for all services, enabling them to communicate by service name. Explicitly defining a network gives you more control. Key Docker Compose commands. Once you have your Docker Compose YAML file, managing your multi-container application becomes incredibly simple. Docker Compose up. This is your main command. It reads the Docker Compose YAML file, builds any images if build is specified, if they're not already built, or if the Docker file has changed. Creates networks and volumes if they're not explicitly marked as external. And finally, it starts all the services defined in your file. By default, it runs in foreground mode, showing service logs in your terminal. Press Ctrl+C to gracefully stop all services. Docker Compose up D. Runs Docker Compose up but in detached mode daemon. All services run in the background, freeing up your terminal. Docker Compose PS. Lists the services in your Compose application, showing their status, running, exited, and exposed ports. Docker Compose Stop stops running services without removing them. You can later restart them with Docker Compose Start. Docker Compose Start stop services. Docker Compose Down. This is the cleanup command. It stops all services associated with the Compose file. It removes the containers. It removes the default network created by Compose. By default, it does not remove volumes. To remove named volumes, like our DB data, you need to add the V flag, Docker Compose Down V. Use this with caution, as it will delete all data stored in those volumes. Docker Compose Logs Service Name. Displays the logs from all services or from a specific service. Add F to follow logs in real time. Docker Compose Build explicitly builds or rebuilds the images for services that have a build instruction. Useful if you've changed the Docker file and want to rebuild the image without starting the services. Docker Compose Exec Service Name Command executes a command inside a running service container, similar to Docker Exec. For example, Docker Compose Exec Web Bash to get a shell inside the web container. Hands-on example. A full web stack, Node.js plus PostgreSQL. Let's bring our Node.js app and PostgreSQL database together using Docker Compose. Project structure, my full stack app. App, a Dockerfile, a app.js, a package.json. Docker Compose YAML. App/Dockerfile from Chapter 4. From Node, 18 Alpine. wrkdir/usr/src/app. Copy package.json. Run npm install. Copy. Expose 3000. cmd npm. Start. App/app.js modified to connect to PostgreSQL. This is a simplified example. A real app would use a more robust way to handle environment variables and database connections. Const express equals require express. Const client equals require PG. PostgreSQL client library. Const app equals express. Const port equals 3000. Database connection details from environment variables. Const client equals new client. User process mdbusr. Host process mdbhost. This will be DB, the service name. Database process mdbname. Password process mdbpasswrd. Port process mdbport. Connect to the database when the app starts. Client.connect error equals if console error database connection error stack. Else console log, connected to database, apt-get/async rec raise equals, try, const result equals await client query, select now, as current time, res send hello from Node.js, current time from DB, result row 0 current time, catch error, console error executing query, stack, res status 500, send error accessing database, app listen port equals, console log, app listening at HTTP localhost, $port, app/package.json, add PG dependency, name Node Docker app, version 1.0.0, description, a simple Node.js web server, main app.js, script, start, Node app.js, dependencies, express 4.17.1, PG 8.7.3, add this line, Docker compose YAML in the root my full stack app directory, version 3.8, services, web build, app build from the Dockerfile in the app directory, ports 80803000, environment nodnv, development, dbhost, db service name db maps to the database container, dbnme, my database, dboscr, user, dbpsswrd, password, dbport, 5432. Depends in is generally sufficient for local dev. For production, add health checks. Depends in, db. Volumes, /app, /usr/src/app, mount local code for live development. db, image, Postgres, 13 using official Postgre SQL image. Environment, postgresdb, my database, postgresUSER. User, postgresbsswrd, password. Volumes, db data, /var/lib/postgresql/data mount named volume for data persistence. Volumes, db data, steps to run, navigate. Open your terminal and navigate to the my full stack app directory where Docker Compose YAML resides. Start the stack, Docker Compose up. You'll see output from both the web and DB services. The DB service should start first, then the web service. Look for signs that the Node.js app successfully connected to the database. Access. Open your browser and go to http localhost:8080/. You should see hello from Node.js, current time from DB, current time. This confirms your web app is talking to the database. Experiment. In a new terminal, try Docker Compose PS to see both containers running. Try Docker Compose logs web to see just the web app's logs. Press Ctrl+C in your original terminal to stop the stack. Clean up, Docker Compose down V. This will stop and remove the containers, the network, and the DB data volume, deleting your database content. Use cases for Docker Compose. Docker Compose shines in several scenarios. Local development environments. This is its strongest suit. Spin up a complete local development environment with all required services, database, message queue, authentication service, etc. Automated testing. Use Compose to bring up a consistent test environment for integration tests in CI/CD pipelines. Single host deployments. For smaller applications or staging environments, Compose can be used to deploy the entire application to a single server. Prototyping. Quickly stand up a complex application stack for proof of concept work. While Docker Compose is excellent for managing multi-container applications on a single host, it's generally not used for managing large-scale, distributed production deployments across multiple hosts. For that, you need more robust orchestration tools like Kubernetes, which we'll briefly introduce in the next chapter. Key takeaways. Docker Compose is a game changer for managing multi-service applications. It simplifies defining and managing interconnected Docker services using a single Docker Compose YAML file. You can define services, networks, and volumes in one place. It provides a streamlined command line interface to start, stop, and clean up your entire application stack. It enables automatic service discovery within its created network, allowing services to communicate by name. It is an indispensable tool for local development environments and automated testing. You've now learned how to define and run a complete multi-container application stack. This truly unlocks the power of Docker for real-world application development. In our next chapter, we'll shift our focus from running applications to sharing them, exploring Docker registries and how to distribute your custom images. Chapter 7, sharing your creations, Docker registries and image distribution. You've built your custom Docker images, you've mastered orchestration with Docker Compose, and your applications are running smoothly in their containerized environments. Now what? The true power of containerization, especially in collaborative or production settings, lies in its ability to facilitate consistent and efficient distribution. How do you get your handcrafted images from your local machine to your teammate's computer, a testing server, or a production cluster? The answer lies in Docker registries. Think of a Docker registry as a centralized digital warehouse for Docker images. Just as a physical warehouse stores goods ready for distribution, a Docker registry stores images ready to be pulled by anyone who needs them. This mechanism is fundamental for enabling collaboration. Teams can share images seamlessly, ensuring everyone works with the exact same application versions and dependencies. Continuous integration, continuous deployment, CI/CD. Automated pipelines can push newly built images to a registry and then pull them down for testing or deployment, creating a smooth, consistent workflow. Consistency across environments ensures that the image run in development is the exact same image run in staging and production, eliminating "it works on my machine" issues at scale. Introducing Docker registries. A Docker registry is a stateless, scalable server-side application that stores and distributes Docker images. It allows users to push images, upload them, and pull images, download them. There are two main types of registries: public registries, accessible to everyone. The most well-known is Docker Hub, private registries, used within organizations to store proprietary or sensitive images securely. Docker Hub, the largest public registry. Docker Hub is the default and largest public registry for Docker images. It's where you've been implicitly pulling images like Nginx, Postgres, and Node, 18 Alpine from throughout this book. Docker Hub also provides a platform for individuals and organizations to share their own public images or pay for private repositories. Your Docker Hub account. To push your own images to Docker Hub, you first need an account. If you don't have one, visit hub.docker.com and sign up. Authenticating with Docker Hub. Before you can push an image, you must authenticate your Docker client with Docker Hub. Docker login. You'll be prompted for your username and password. If successful, you'll see "Login succeeded." This command stores your credentials so you don't have to enter them for every push. Understanding repositories. On Docker Hub, images are organized into repositories. A repository is a collection of images with the same name but different tags, versions. For personal accounts, repositories are typically named username/repository name. For example, myname/myweb-app. Image tagging, preparing for push. Before you can push an image, it needs to be tagged with a name that includes the registry's hostname. If it's not Docker Hub, and your repository name. For Docker Hub, this format is usually your username/your repo name, tag. Recall our Node Web App image from Chapter 4, which we built and tagged as Node Web App 1.0. To push this to Docker Hub, we need to retag it with our Docker Hub username. Let's assume your Docker Hub username is mydev. Docker tag Node Web App 1.0 mydev/Node Web App 1.0. This command creates a new tag, an alias, pointing to the same image ID. No new image is built or created. It's simply a pointer. You can verify this by running Docker images. You'll see two entries for the same image ID. You can also tag an image immediately during the build process. Docker build t-mydev/Node Web App 1.0. Pushing images to Docker Hub. Once your image is tagged correctly, pushing it is simple. Docker push mydev/Node Web App 1.0. Docker will then upload the image layers to Docker Hub. If the base layers, like Node, 18 Alpine, already exist on Docker Hub, they won't be re-uploaded, demonstrating the efficiency gains of Docker's layered architecture even in distribution. After the push completes, you can log into hub.docker.com with your web browser, navigate to your repositories, and you should see mydev/Node Web App listed with the 1.0 tag. Pulling your own images. Once your image is on Docker Hub, anyone, including yourself on a different machine, can pull it down and run it, simply by knowing its full name and tag. Docker pull mydev/node web app 1.0. Docker run p80803000 mydev/node web app 1.0. This completes the full cycle of building, running, and distributing your custom container images. Private registries, keeping your creations secure. While Docker Hub is excellent for public images, it's not suitable for proprietary applications or sensitive data. For these scenarios, you'll use a private registry. Private registries offer security, control who can access your images. Compliance, meet regulatory requirements for data locality or security standards. Performance, faster image pulls within your private network or cloud environment. Common solutions for private registries include cloud provider container registries. Most major cloud providers offer their own managed container registries. These are highly scalable, secure, and integrate seamlessly with their other services, e.g., AWS Elastic Container Registry, ECR, Google Container Registry, GCR/Artifact Registry, Azure Container Registry, ACR. Self-hosted registries. You can run your own Docker registry server. Tools like Harbor or the open-source Docker registry implementation allow you to host images on your own infrastructure. This offers maximum control, but requires more operational overhead. The process of interacting with a private registry is very similar to Docker Hub. Login. You first log in to the specific registry's domain, e.g., Docker login my-private-registry.example.com. Tag your image with the registry's domain as part of the name e.g. Docker tag my local image, my-private-registry.example.com/project/my-image:1.0. Push-pull, use Docker push and Docker pull as normal. Security considerations for image distribution. Sharing images is powerful, but it also introduces security considerations. Sensitive data. Never include sensitive information, API keys, passwords, private SSH keys, directly in your Dockerfiles or baked into your images. Use environment variables, which can be passed securely at runtime or Docker secrets, for orchestrators like Docker Swarm or Kubernetes. Vulnerability scanning. Regularly scan your images for known vulnerabilities. Many registries, Docker Hub included, offer integrated scanning features. For instance, Docker Scan can integrate with Snike to identify vulnerabilities. Least privilege. Use the smallest possible base images and ensure your containerized applications run with the minimum necessary permissions. Run as a non-root user whenever possible, as touched on in Chapter 4, and will be explored further in Chapter 9. Image provenance. Be careful about images you pull from untrusted sources. Authenticated and verified publishers can help ensure image integrity. Think of images as executable binaries you distribute. You wouldn't download a random executable from the internet and run it without caution, and the same applies to Docker images. Key takeaways. Image distribution through registries is the backbone of collaborative and automated container workflows. Docker registries are centralized storage locations for Docker images. Docker Hub is the largest public registry, essential for accessing and sharing common community images. You must tag your local images with the correct repository name, including your username or organization, before you can push them to a registry. Private registries are crucial for secure and efficient distribution of proprietary images within organizations. Always be mindful of security best practices when building and sharing images, avoiding sensitive data and minimizing attack surfaces. You've now learned how to build, run, manage, and share your containerized applications. This solidifies your ability to work with Docker professionally. Now that you can handle single-host multi-container setups with Docker Compose, you might wonder, what about deploying and scaling applications across many servers? That leads us into the realm of container orchestration, which we'll briefly explore in the next chapter. Chapter 8, Scaling Up, a glimpse into container orchestration, Kubernetes introduction. Thus far, our journey has focused on Docker's incredible power for single-host environments. You've harnessed containers for consistency, isolation, and portability. You've orchestrated multi-service applications locally using Docker Compose, creating seamless development setups. But what happens when your application needs to serve millions of users? When it needs to handle fluctuating traffic, recover automatically from failures, and deploy updates without downtime. Running a few containers on a single machine is manageable. Running hundreds or thousands of containers across a cluster of many machines is a completely different ballgame. This is where container orchestration systems come into play. Limitations of Docker: Compose for production at scale. Docker Compose is fantastic for local development, testing, and even simple, single-server deployments. However, it wasn't designed for the complexities of large-scale production environments. No high availability. If the single server running your Compose application goes down, your entire application is offline. Compose has no built-in mechanisms to restart containers on a different machine. No dynamic scaling. Scaling an application would involve manually starting more containers on the same host, which eventually hits resource limits, or manually replicating the Compose setup on new servers. No self-healing. If a container crashes, Compose won't automatically restart it on a healthy machine. No load balancing across multiple instances. While Compose can expose ports, it doesn't automatically distribute incoming traffic across multiple running instances of the same service for robust load balancing. Limited rollouts rollbacks. Deploying updates or rolling back to a previous version is a manual process that can cause downtime. These limitations highlight the need for a more sophisticated system to manage containers in a distributed, resilient, and scalable manner. This is precisely what container orchestrators do. What container orchestration solves? Container orchestration is the automated management, deployment, scaling, networking, and availability of containerized applications. An orchestrator helps you manage the lifecycle of your containers, ensuring they run where and when you want them to, and that they can recover from failures. Here's what an orchestrator typically handles: deployment. Defining how your application images, configurations, resources should be deployed across a cluster of machines. Scheduling. Deciding which machine node in the cluster should run a specific container instance based on resource availability, constraints, and other factors. Scaling. Automatically or manually increasing or decreasing the number of container instances based on demand. High availability and self-healing. If a container or even an entire machine fails, the orchestrator detects the failure and automatically restarts containers on healthy nodes. Service discovery and load balancing, making it easy for containers to find and communicate with each other and distributing incoming traffic across multiple healthy instances of a service. Configuration management, securely managing and injecting sensitive data, like database passwords, and application-specific settings into containers. Updates and rollbacks, rolling out new versions of applications gradually without downtime, and easily reversing to a previous version if issues arise. Resource management, allocating CPU, memory, and other resources to containers to prevent resource contention. Introduction to Kubernetes, the industry standard. While there are several container orchestration tools, Docker Swarm, Apache Mesos, HashiCorp Nomad, Kubernetes, often abbreviated as K8s, has emerged as the undisputed leader and industry standard. It's an open-source system originally designed by Google, and it powers many of the world's largest internet services. Kubernetes is not another Docker replacement. Instead, it works with Docker or other container runtimes to manage your containerized applications at scale. Docker builds the individual ships. Kubernetes manages the entire armada. Key Kubernetes concepts, high-level overview. Understanding Kubernetes requires learning its unique terminology and architecture. We'll only touch upon the most fundamental concepts here to give you a conceptual understanding. Cluster. At its core, Kubernetes operates on a cluster of machines. These machines are divided into master nodes, control the cluster, schedule workloads, and manage the overall state. Worker nodes or minions, the machines where your actual containers run. Pods, the smallest deployable unit in Kubernetes. A pod is a single instance of a running process in your application. Crucially, a pod can contain one or more tightly coupled containers that share resources like network and storage. If you have a primary application container and a sidecar container, e.g., a logging agent that always run together, they typically reside in the same pod. Deployments, a higher-level abstraction that defines how to run and scale your application. A deployment tells Kubernetes which Docker images to use, how many replicas, identical pods of your application should be running, how to handle updates, e.g., rolling updates that gradually replace old pods with new ones, ensuring zero downtime. When you create a deployment, Kubernetes automatically takes care of creating the necessary pods and ensuring the desired number of replicas are always running. Services, in Kubernetes, pods are ephemeral, meaning they can be created and destroyed dynamically, e.g., during scaling or self-healing. This means their IP addresses can change. A Kubernetes service provides a stable network endpoint, a static IP address and DNS name for a set of pods. It acts as a load balancer for a group of pods, distributing incoming traffic amongst them. It enables service discovery, allowing other applications in the cluster to find and communicate with your application using its stable service name, without needing to know the individual pod IP addresses. Namespaces provide a way to virtually partition a cluster into subclusters. This is useful for organizing resources, separating environments, e.g., development, staging, production, or isolating teams within a larger cluster. How Kubernetes compares to Docker Compose. While both deal with multi-container applications, their scope and capabilities differ greatly. Feature Docker Compose Kubernetes. Scope single-host multi-container apps, local dev. Test, multi-host distributed clusters, production, large-scale. Deployment manual via Docker, Compose up automated. Declarative deployment with self-healing. Scaling manual multiple Docker run calls, or upscale, automated with deployments. Horizontal pod auto-scaling, HPA. High availability, only if host is highly available built-in. Self-heals, restarts on healthy nodes. Load balancing basic port mapping to host advanced. Built-in load balancing for services and ingress. Complexity relatively simple. YAML config significant learning curve. Many concepts and abstractions. Resource MGMT. Basic e.g., CPU memory limits in Compose file, advanced requests, limits, scheduling based on node resources. Updates, restart containers, rolling updates. Blue-green deployments, canary releases. Tools Docker Compose CLI, Kubectl CLI. Extensive dashboard and ecosystem tools. When do you need Kubernetes? You don't need Kubernetes for every project. For many small to medium applications, a single server running Docker and Docker Compose, or even just individual Docker containers, might be perfectly sufficient and simpler to manage. You should consider moving to Kubernetes when high availability is critical. Your application cannot tolerate downtime. Your application needs to scale dynamically. Your user base or traffic fluctuates significantly. You have a complex microservices architecture. Managing many interdependent services across multiple teams becomes a nightmare without automated orchestration. You're managing a large number of applications containers. Centralized management becomes a necessity. You're building for cloud-native environments. Kubernetes is the de facto standard for deploying applications in public or private clouds. A look at Docker Swarm, brief mention. Before Kubernetes became dominant, Docker had its own orchestration solution called Docker Swarm or Swarm Mode. It's built directly into Docker Engine and allows you to form a cluster, swarm of Docker hosts. It's generally simpler to set up and manage than Kubernetes, making it a good choice for those who need basic multi-host clustering capabilities without the full complexity of Kubernetes. However, Kubernetes' ecosystem, features, and community support are far more extensive. Docker Swarm remains a viable, simpler alternative for specific use cases. Key takeaways. While this chapter only provides a conceptual peek, it's vital to recognize the scope and purpose of container orchestration. Docker Compose is for single-host, multi-container management, primarily for development and smaller deployments. Container orchestration is about automating the management of containers across clusters of machines for high availability, scalability, and resilience. Kubernetes is the leading container orchestrator, used for large-scale, production-grade deployments. Key Kubernetes concepts include pods, deployments, and services, which together provide powerful abstractions for managing distributed applications. Understanding when to use an orchestrator and which one is as important as knowing how to use it. You now have a clearer understanding of the broader Docker ecosystem and where your skills lie on the path to managing production-grade containerized applications. In the upcoming chapters, we'll shift our focus to practical considerations like best practices for building secure and efficient containers, real-world case studies, and essential troubleshooting techniques. Chapter 9, Best Practices: Security, Efficiency, and Maintainability. You've learned to build, run, manage, share, and even glimpse the large-scale orchestration of Docker containers. With great power comes great responsibility. And in the world of Docker, this translates to implementing best practices for security, efficiency, and maintainability. Building Docker images and running containers isn't just about making them work. It's about making them work well, making them lean, and making them safe. Neglecting these aspects can lead to bloated images, slow deployments, resource waste, and most critically, security vulnerabilities that could expose your applications or data. This chapter will guide you through essential guidelines and techniques to ensure your Docker usage is robust and reliable. 1. Security best practices. Security in Docker is multifaceted, covering everything from the base image you choose to how your application runs inside the container. 1.1. Choose a minimal base image. Why? Smaller base images, like Alpine or Slim variants, reduce the attack surface. They contain fewer packages, fewer binaries, and fewer potential vulnerabilities. They also result in smaller final image sizes, which speeds up downloads and deployments. How? Use from Alpine or from Node, 18 Alpine instead of from Ubuntu or from Node, 18. 1.2. Run as a non-root user. Why, by default, processes inside a container run as the root user. If an attacker manages to escape the container, a container escape, they gain root privileges on the host system. Running as a non-root user greatly mitigates this risk by limiting the attacker's privileges even if they compromise the container. How? Create a dedicated user in your Dockerfile. Run a user system, no create home abuser. Set the user instruction to this new user after any commands that require root privileges, e.g., apt-get install, npm install. Hash example for Node.js. From Node, 18 Alpine. wrkdir app. Copy package JSON. Run npm install production, hash install production dependencies. Copy. Run a user system, no create home abuser hash, create user. User abuser hash, switch to non-root user. CMD node, app.js. 1.3. Avoid installing unnecessary packages. Why? Every extra package or dependency added to your image increases its size and the potential for new vulnerabilities. Only install what your application absolutely needs to run. How? Remove build dependencies after installation. If using apt-get, combine apt-get update, installation, and rm/rf var/lib/apt/list/ in a single run instruction. Leverage multi-stage builds, see next section, to achieve this effectively. 1.4. Scan your images for vulnerabilities. Why? Software vulnerabilities are discovered constantly. Regularly scanning your images helps identify known security flaws in your base images and dependencies. How? Integrate image scanning into your CI/CD pipeline, e.g., using tools like Snike, Claire, Trivy. Docker Desktop includes a Docker scan command which uses Snike to perform basic vulnerability scans on your images. Many private registries, AWS ECR, Azure ACR, also offer built-in scanning capabilities. 1.5. Use specific image tags, avoid latest in production. Why? The latest tag is mutable. It can point to different versions of an image at different times. This means your builds might not be reproducible. Using specific tags, e.g. Node 18.17.0 Alpine, ensures consistency. How? Always specify exact version tags in your from instructions and when pushing images. 1.6. Don't store secrets directly in images or Dockerfiles. Why? Hardcoding passwords, API keys, or database credentials makes them visible to anyone with access to the image. How? Use environment variables passed at runtime, e.g., Docker run emysecret equals value. Docker secrets for Docker Swarm/Kubernetes, or external secret management services, e.g., HashiCorp Vault, AWS Secrets Manager. 2 efficiency best practices: image size and build speed. Lean images are faster to build, push, pull, and deploy. They also consume less disk space. 2.1. Leverage multi-stage builds. Why? This is arguably the most powerful technique for building small, production-ready images. It allows you to use one image for building your application, with all its compilers, SDKs, and build tools, and then copy only the essential compiled artifacts into a much lighter final image. This prevents build tools from ending up in your final runtime image. How? As shown in Chapter 4, use multiple from instructions and copy from to transfer artifacts. Hash example. Multi-stage build for a Go application. From Golang 1.20 Alpine as builder. WRKDIR app. Copy, run go build MyApp. From Alpine latest. WRKDIR app. Copy from equals builder/app/MyApp. CMD/MyApp. 2.2. Use Docker ignore. Why? Prevents unnecessary files like node modules from your host, Git repositories, IDE files, or temp directories from being sent to the Docker daemon as part of the build context. This speeds up the build context transfer and ensures these files don't accidentally get copied into your image. How? Create a Docker ignore file in the same directory as your Docker file and list patterns of files directories to exclude, similar to git ignore. Hash Docker ignore example. Git, node modules, npm debug log, ds store, tmp. 2.3. Minimize the number of layers. Why? While building a new layer for each instruction is generally efficient due to caching, too many layers can slightly increase image size and build time. How? Combine related run instructions using and to execute multiple commands within a single layer. Hashbad creates 2 layers. Run apt-get update. Run apt-get install yMyPackage. Hashgood creates a single layer. Run apt-get update and in /. apt-get install yNoInstall recommends myPackage and in /. rm rf var/lib/apt/lists/hash cleanup apt cache to keep image small. 2.4. Order instructions optimally to leverage cache. Why? Docker caches layers. If an instruction and its context hasn't changed, Docker reuses the cached layer, speeding up subsequent builds. How? Place instructions that change less frequently, e.g., copying package.json for dependency installation, before instructions that change often, e.g., copying your application's source code, copy. Hash optimal ordering for Node.js app. From Node 18 Alpine. WRKDIR app. Copy package.json. Hash copies only package files first. Run npm install. Hash this layer is reused if only app code changes. Copy. Hash copies app source code. CMD node, app.js. 3 maintainability best practices. Well-structured Dockerfiles and container configurations make your system easier to understand, manage, and debug. 3.1. Document your Dockerfiles. Why? Comments in your Dockerfile explain the purpose of instructions, making it easier for others and your future self to understand and maintain. How? Use hash for comments. Hash use the official Python image from Docker Hub. From Python 3.9 Slim Buster. Hash set the working directory for subsequent instructions. WRKDIR app. Hash copy the application's dependencies first to optimize layer caching. Copy requirements.txt. Run pip install r requirements.txt. Hash copy the rest of the application code. Copy. Hash expose the port the Flask app runs on documentation only. Expose 5000. Hash define the default command to run the application. CMD Python appy. 3.2. Use labels. Why? Labels are key value pairs that can be added to Docker images to embed metadata. This can include maintainer info, version control details, or build dates. How? Use the label instruction. Label maintainer equals your name, your email at example.com. Label version equals 1.0.0. Label description equals my awesome web app. 3.3. Standardize environment variables. Why? Use consistent naming conventions for environment variables across your services for configurations like database connections, API keys, etc. How? Document required environment variables wherever your application is deployed, e.g., in Docker Compose YAML or Kubernetes deployment manifests. 3.4. Implement health checks. Why? For services in a multi-container application, especially with Docker Compose or orchestrators, it's crucial to know if a container's application is actually healthy and ready to serve requests, not just that the container process is running. How? Use the HEALTHCHECK instruction in your Docker file. It specifies a command to run periodically inside the container to check its health. Hash example for a web server. HEALTHCHECK interval equals 30s timeout equals 10s retries / CMD curl fail HTTP localhost exit 1. Or in Docker Compose YAML. Services web hash health check test CMD curl fail HTTP localhost / interval 30s timeout 10s retries 3. 4. Logging and monitoring considerations. While not directly built into the Docker file, understanding how to handle logs is critical for maintainability and debugging. 4.1. Write logs to standard output error stdout / stdir. Why? Docker is designed to capture and manage logs from containers that write to stdout and stdir. This allows central log aggregation tools to easily collect and process your application's logs. How? Configure your application to log to the console instead of writing to local files within the container. For example, in Node.js, use console log and console error. For Nginx, configure access error logs to /dev/stdout and dev/stdir. You can then use Docker logs containerid to view them or integrate with logging drivers and external services. Key takeaways. Implementing best practices from the start will save you significant headaches down the line. Remember, security, always prioritize running as non-root, choosing minimal base images, and regularly scanning for vulnerabilities. Never hardcode secrets. Efficiency. Optimize image sizes and build times with multi-stage builds, Docker ignore, careful instruction ordering, and minimizing layers. Maintainability. Document with comments and labels, standardize configurations, and implement health checks for robust operation. Logging. Direct your application logs to stdout / stdir for easy collection by Docker and external logging systems. By adhering to these guidelines, you'll be building Docker images that are not just functional, but also secure, efficient, and easy to manage throughout their lifecycle. In the next chapter, we'll dive into practical applications and real-world case studies to see how these concepts come alive in different scenarios. Chapter 10. Real-world voyages. Practical applications and case studies. By now, you've acquired a comprehensive understanding of Docker, from its core concepts and syntax to building images, orchestrating multi-container applications, sharing your creations, and even best practices for security and efficiency. But how does all this translate into real-world scenarios? This chapter aims to solidify your understanding by showcasing practical applications and case studies of Docker containers across various domains. Seeing how Docker addresses common challenges and enables powerful new workflows will not only reinforce what you've learned, but also inspire you to apply these skills in your own projects. 1. Streamlining development environments. One of Docker's most immediate and widespread benefits is providing consistent and reproducible development environments. The "it works on my machine" problem, discussed in Chapter 1, is directly solved here. Scenario: a development team works on a web application that requires Node.js, PostgreSQL, and Redis. Each developer has a different operating system, Windows, macOS, Linux, and varying versions of tools installed locally. Onboarding a new developer takes days just to set up their machine correctly. Docker solution. The team defines their entire development stack in a Docker Compose YAML file. This file specifies the exact versions of Node.js, PostgreSQL, and Redis images, along with any necessary configurations, volumes for data persistence, and environment variables. Outcome: consistency. Every developer runs the application in the exact same environment, eliminating "it works on my machine" issues. Rapid onboarding. A new developer can clone the repository, run Docker Compose Up, and have a fully functional development environment within minutes, regardless of their host OS setup. Dependency isolation. Docker containers prevent conflicts between different project dependencies, e.g., if one project needs Node.js 16 and another needs Node.js 18. Ease of experimentation. Developers can quickly spin up isolated instances of services for testing new features or debugging without affecting their main environment. 2. Revolutionizing CI/CD pipelines. Continuous integration, CI, and continuous delivery deployment, CD, are practices designed to automate the build, test, and deployment processes. Docker has become a cornerstone of modern CI/CD pipelines. Scenario: a large software project has automated tests that need to run whenever new code is pushed. These tests require a specific testing environment, e.g., Python 3.9, a particular database schema, and browser automation tools. Setting up and tearing down this environment for every test run is slow and resource-intensive, and inconsistencies often lead to flaky tests. Docker solution: build stage. The CI server uses a Dockerfile to build the application's Docker image, ensuring all dependencies are packaged consistently. Test stage. The CI server spins up a multi-container environment using Docker Compose. This includes the application's container, a test database container, and any other required services. Test runners execute within a dedicated container or against the application container. The entire test environment is isolated and ephemeral, created for each test run and discarded afterward. Deployment stage. Once tests pass, the application's Docker image is pushed to a Docker registry, e.g., Docker Hub or a private cloud registry. Later, this image is pulled by a deployment tool like Kubernetes and deployed to production. Outcome: reproducible tests. Tests run in precisely the same environment every time, reducing flaky tests caused by environmental differences. Faster feedback. Automated environment setup and teardown improve CI efficiency. Simplified deployments. The built Docker image becomes the deployable artifact, ensuring that what was tested is exactly what gets deployed. Resource efficiency. CI/CD runners only need Docker installed, not all the project's specific dependencies. 3. Containerizing legacy applications, lift and shift. Many organizations have existing, monolithic applications that are difficult to update, deploy, or scale. Docker offers a pathway to modernize these legacy applications without a complete rewrite. Scenario: a company has a critical business application developed years ago with outdated dependencies, running on an old version of an operating system. Maintaining the legacy server environment is costly, and migrating it to a modern cloud infrastructure is challenging. Docker solution. The legacy application, along with all its specific dependencies, e.g., older Java runtime environments, specific library versions not compatible with newer OSes, is packaged into a Docker image. This process might involve creating a Dockerfile that replicates the exact environment found on the original server. Outcome: portability. The legacy application can now run on any modern Linux server with Docker or within a cloud environment, disentangling it from its original, aging infrastructure. Isolation. The legacy app is isolated from other applications, preventing dependency conflicts or security vulnerabilities from propagating. Simplified maintenance. While not a full modernization, containerizing allows for easier patching of the underlying OS, and the application is isolated from other system-wide changes. It's a stepping stone to microservices or eventual rewrites. Cost savings. Running on modern, commodity hardware or cloud instances can be more cost-effective than maintaining specialized legacy servers. 4. Microservices architectures. As hinted in Chapter 1 and expanded on in Chapter 8, Docker is arguably the best technology for implementing microservices architectures. Each microservice, a small, independent, loosely coupled service, can be deployed as its own Docker container. Scenario: a large e-commerce platform is built as a single, massive monolithic application. A small change in the product catalog module requires redeploying the entire application, which is a lengthy and risky process affecting all parts of the system. Docker solution. The monolith is refactored into independent microservices, e.g., product catalog service, order processing, user authentication, payment gateway. Each microservice is developed, deployed, and scaled as an independent Docker container. These containers communicate over defined APIs. Kubernetes, or similar orchestrators, manages the deployment and scaling of these services across a cluster. Outcome: independent deployment. Each service can be updated and deployed independently, reducing deployment risk and allowing continuous delivery. Scalability. Individual services can be scaled up or down based on their specific demand, optimizing resource utilization. Technology heterogeneity. Different services can be written in different programming languages or use different technologies, choosing the best tool for the job. Improved resilience. The failure of one microservice does not necessarily bring down the entire application. 5. Local testing and debugging. For developers, Docker dramatically simplifies local testing and debugging by providing consistent environments. Scenario: a developer needs to test their application against a specific version of a database, e.g., MongoDB 5.0, or a message queue, e.g., RabbitMQ. Installing these locally can be complex and conflict with other projects. Docker solution. The developer simply pulls the official MongoDB 5.0 or RabbitMQ image from Docker Hub and runs it in a container. They can then connect their local application code to this containerized service. Outcome: clean local machine. Developers don't need to clutter their local systems with various installations and configurations of databases, queues, or other services. Isolated testing. Test against a clean, isolated instance of the service, ensuring tests are consistent and reproducible. Version flexibility. Easily switch between different versions of external services by simply changing the Docker image tag. 6. Packaging and distributing standalone applications. Docker isn't just for web services. It's also a great way to package and distribute command line tools, batch jobs, or scientific applications that have complex dependencies. Scenario: a data scientist develops a complex statistical model that requires numerous Python libraries, specific C++ compilers, and large data files. Sharing this model with colleagues or deploying it in a production pipeline is difficult due to dependency management. Docker solution. The data scientist creates a Dockerfile that includes the base operating system, installs all necessary Python scientific libraries, includes the model's code, and perhaps even some initial data. Outcome: reproducible research. Ensures that scientific results are reproducible by packaging the entire computational environment. Simplified deployment. The model can be run consistently on any machine with Docker, from a colleague's laptop to a cloud-based compute cluster, without needing to manually set up the environment. Dependency management. All complex dependencies are encapsulated within the image, simplifying deployment to diverse environments. Key takeaways. These real-world examples demonstrate Docker's versatility and transformative impact across the software development lifecycle. It helps developers by providing consistent environments, speeding up onboarding, and simplifying local testing. It empowers operations teams with consistent deployment artifacts, improved scalability, and resilience. It provides a clear path for modernizing legacy applications and enables agile development with microservices. It simplifies the packaging and distribution of any application with complex dependencies. As you can see, Docker is far more than just a tool for virtualizing applications. It's a fundamental shift in how we build, ship, and run software. Your understanding of these practical applications should give you the confidence to apply Docker in your own projects. In the next chapter, we'll equip you with troubleshooting and debugging skills, preparing you to navigate the inevitable challenges that arise when working with complex systems. Chapter 11: Troubleshooting and Debugging. Navigating stormy seas. Even with the best practices and a solid understanding of Docker's fundamentals, issues will inevitably arise. Containers might fail to start, applications within them might crash, or services might refuse to communicate. Just like any complex system, Docker can be finicky at times. But thankfully, Docker provides a powerful set of tools and commands to help you diagnose and resolve these problems. This chapter will arm you with the essential techniques and common debugging strategies to navigate these stormy seas and get your containers back on course. General approach to troubleshooting. Before diving into specific commands, adopt a systematic approach to debugging. Observe what exactly is the symptom. Is the container not starting? Is it crashing? Are logs missing? Is a service unreachable? Locate which component is failing. Is it the Docker daemon, the image itself, the application inside the container, or the network? Inspect, gather as much information as possible. Look at logs, inspect container details, and check resource usage. Hypothesize and test. Based on your observations and inspection, form an idea of what might be wrong, and then test your hypothesis. Iterate. If your first hypothesis is wrong, gather more information and try another. Common problems and their solutions. Let's explore some of the most frequent issues you'll encounter and how to tackle them. 1. Container fails to start or exits immediately. This is perhaps the most common and frustrating issue for new Docker users. A container seemingly starts, but then immediately disappears or shows an exited status. Symptom: Docker PS shows no running container, or Docker PSA shows the container in an exited state. Likely cause: the application inside the container terminated unexpectedly, or the cmd entrypoint in the Dockerfile did not result in a long-running process. Debugging steps: check logs, Docker logs. This is your first and most important step. The application inside the container might have printed an error message to stdout or stdir before exiting. Docker logs container reader name. Look for error messages, stack traces, or configuration problems. Inspect container details, Docker inspect. This command provides comprehensive metadata about the container, including its exit code. A non-zero exit code indicates an error. Docker inspect container reader name, grep exit code. Also check the state and error fields. Run in interactive mode with a shell Docker, run it rm or docker exec, it. If you suspect a missing dependency or an issue with the application's startup command, try running the container in interactive mode or attaching to it. Hash for a new container, trying to debug startup. Docker run it rm image name bash hash or sh. If bash is not an image, hash once inside, try to manually run your application's start command, e.g. node app.js. Hash this allows you to see errors directly, install missing packages, etc. Hash for an existing, stopped container, Docker start container reader name, Docker execute container reader name bash. Verify cmd/entrypoint. Ensure your Dockerfiles cmd or entrypoint is correctly specified and actually starts the main application process. Remember the difference between exec form, executable, arg, and shell form, executable arg. Shell form runs the command in a shell, which can sometimes be helpful, e.g., for piping, but exec form is generally preferred because it launches the process directly. 2. Port conflicts or service unreachable. You've started a container, but you can't access its service from your host machine or from another container. Symptom: browser shows connection refused, curl fails, or other containers can't connect. Likely causes: incorrect port mapping, firewall issues, service not listening on the correct IP port inside the container, or network configuration problems. Debugging steps: check port mapping, Docker PS. Make sure the P or ports in compose port mapping is correct. Is hostport, container port what you intended? Docker PS. Hash look at the ports column, e.g. 0.0.0.0:8080 3000/TCP. Check if service is listening inside container, Docker exec. Is the application inside the container actually listening on the expected port and IP address? Docker execute container reader name ss-toln hash or netstat-toln. This lists listening ports. You should see your application listening, often on 0.0.0.0 all interfaces, or IP6 all interfaces on the container's designated port. If it's listening on 127.0.0.1 localhost, it won't be accessible from outside the container. Check container network configuration, Docker inspect/Docker network inspect. If containers can't communicate with each other, confirm they are on the same bridge network, custom network created by Docker Network Create or Docker Compose. Verify you're using the correct service name or container name as the hostname. Docker inspect container reader name hash, look under Networks section for IP address. Docker network inspect network name hash see which containers are connected and their IPs. Firewall. Ensure your host's firewall isn't blocking the hostport you're trying to access. Temporarily disabling the firewall can help diagnose. DNS resolution. If using service names, check if DNS resolution is working within the network. Docker execute container retrieve to connect, ping target service name. 3 image build failures. Your Docker build command fails somewhere in the Docker file. Symptom. Build process stops with an error message, often during a run instruction. Likely cause, command syntax error, missing dependencies during build, network issues preventing package downloads, or incorrect file paths. Debugging steps, read the error message. Docker's build output is often quite verbose and points directly to the failing step. Look for the running in containerized line to identify the exact instruction. Break down the Docker file. Comment out lines after the failing instruction and rebuild. Gradually uncomment lines to pinpoint the exact problematic command. Build interactively. If a run command is failing, you can sometimes run the build up to the failing layer, then create a temporary container from that layer and try to run the command interactively. Hash suppose build fails at run apt-get install. Hash look for the last successfully built layer's ID, e.g. dseb0bd0b1f2, in build output. Docker run it rm dseb0bd0b1f2 bash hash or sh. Hash now, manually run the failing command inside this temporary container. Hash this lets you see more detailed error messages, fix typos, etc. Docker ignore problems. Sometimes files you expect to be copied aren't there because they're excluded by a Docker ignore rule. Check your Docker ignore file for data loss or data not persisting. You restart a container, and your data is gone or database changes aren't saved. Symptom, application reports missing data after container restart recreation. Likely cause, not using volumes or bind mounts or using them incorrectly. Data was written only to the container's ephemeral writable layer. Debugging steps. Verify volumes, bind mounts. Check your Docker run v or Docker composable volumes section. Is the host path or volume name correctly mapped to the target path where the application writes data inside the container? Inspect container mounts. Docker inspect container reader name. Hash look for mounts section to see what volumes bind mounts are attached and their source destination. Check volume contents. If you suspect an issue with the data in the volume, you can inspect its contents on the host machine. For bind mounts, go directly to the host path. For named volumes, use Docker volume inspect volume name to find the actual mount path on the host, then navigate there. 5. Resource exhaustion or slow performance. Containers are running very slowly or the host machine is overloaded. Symptom, applications are sluggish, high CPU memory usage on the host. Likely cause, application resource leaks, container misconfiguration, or insufficient host resources. Debugging steps, monitor resources, Docker stats. This command provides a live stream of CPU, memory, network I/O, and block I/O usage for all running containers. Docker stats. Identify which containers are consuming the most resources. Check resource limits reservations. Are you running many containers with no resource limits? In Docker Compose, you can define resources for services, CPU and memory limits reservations. For Kubernetes, this is critical requests and limits. Inspect application logs. Is the application itself exhibiting performance issues, e.g., excessive database queries, infinite loops? Profiling within container. If you can Docker exec into the container, use standard profiling tools for your application's language to identify bottlenecks. Advanced debugging tools and techniques. Docker events, streams real-time events from the Docker daemon, container start-stop, image pull-push, etc. Useful for seeing what Docker is doing behind the scenes. Debug Dockerfile by hand. If a run instruction fails, try to perform the steps one by one manually in a temporary container. This helps isolate exact errors. Hash build up to the problematic layer. Docker build t-tempimage f dockerfile.debug. Hash only contain problematic commands. Hash run the debugger. Docker run it tempimage bash. Hash now execute step by step and debug here, using a debugger inside the container. For more complex application issues, you can often configure your development environment to attach a debugger directly to the process running inside your Docker container. This usually involves exposing a debug port and configuring remote debugging. This is highly application-specific. Key takeaways. Troubleshooting Docker is a skill that improves with practice. Be methodical and follow these key principles. Start with logs. Docker logs is your first line of defense. Inspect deeply. Docker inspect reveals vast amounts of information about your containers and images. Interactive shells. Docker exec at containerized bash is invaluable for poking around inside a running container. Resource monitoring. Use Docker stats to identify performance bottlenecks. Understand container life cycles. Knowing the difference between stopped and removed containers and how CMD and ENTRYPOINT work is crucial. Clean up. Regularly prune unused containers, images, and volumes to avoid clutter and potential conflicts using Docker System Prune. With these tools and strategies, you'll be well equipped to diagnose and resolve a wide array of Docker-related problems, keeping your containerized applications sailing smoothly, even through stormy seas. In our final chapter, we'll look beyond the horizon to the future of containers and discuss next steps for your ongoing learning. Chapter 12. Beyond the Horizon, the Future of Containers and Next Steps. Congratulations! You've journeyed from a fundamental understanding of why Docker matters to building, running, managing, and sharing your containerized applications. You've navigated multi-service deployments with Compose, seen a glimpse of large-scale orchestration with Kubernetes, embraced best practices for security and efficiency, and learned to troubleshoot common issues. This comprehensive voyage has equipped you with skills vital in today's software development landscape. But the world of containers is dynamic. It's constantly evolving, with new tools, practices, and technologies emerging. This final chapter will offer a glance beyond the immediate horizon, covering some emerging trends and providing guidance for your continued learning journey. The Open Container Initiative, OCI. Standardization and choice. One of the most significant developments in the container ecosystem has been the emergence of the Open Container Initiative, OCI. Founded in 2015 by Docker, CoreOS, Google, and others, OCI is a Linux Foundation project aiming to create open industry standards for container formats and runtimes. What it means, instead of Docker being the only way to package and run containers, OCI has standardized the image format, how a container image is structured and stored. Runtime specification, how a container runtime should run an OCI-compliant image. Impact. This standardization has fostered innovation and competition. While Docker Engine remains incredibly popular, other compliant container runtimes like Containerized and CRIO are widely used, especially in orchestration platforms like Kubernetes. It means that an image generated by Docker can be run by Containerized, and so on. This ensures portability and prevents vendor lock-in. Your takeaway: while you've learned Docker, the underlying principles and the widespread adoption of OCI standards mean your skills are transferable beyond Docker itself and extend to the broader container ecosystem. Emerging container technologies and concepts. The container landscape is always pushing boundaries. Serverless containers, the intersection of containers and serverless computing. Platforms like AWS Fargate, Azure Container Instances, ACI, Google Cloud Run, and Native on Kubernetes allow you to run containers without managing the underlying servers. You provide your container image, and the cloud provider handles all the infrastructure, scaling, and operational overhead. This offers the portability of containers with the operational simplicity of serverless. WebAssembly, WASM, and WASI, WebAssembly System Interface. Originally designed for web browsers, WebAssembly is gaining traction as a lightweight, portable runtime for server-side applications. WASM modules are even smaller and start faster than traditional containers. WASI aims to provide system interfaces to WASM, allowing it to interact with file systems, networks, and environment variables. While not replacing Linux containers entirely, WASM is emerging as an attractive alternative for specific workloads, especially for highly distributed, edge computing, or resource-constrained environments. It's an exciting area to watch. eBPF, Extended Berkeley Packet Filter, a powerful technology within the Linux kernel that allows programs to run in a sandboxed environment within the kernel. It's revolutionizing networking, observability, and security for containers. Tools using eBPF enable deep insights into container performance and robust network policies, often with less overhead than traditional methods. Projects like Cilium, for Kubernetes networking, use eBPF extensively. Rootless containers, a significant security enhancement for running containers without requiring root privileges on the host machine. This lessens the impact of a potential container escape. Docker, Podman, and other runtimes now support rootless modes. Beyond Docker and Kubernetes, the broader cloud-native landscape. While Docker and Kubernetes are central, they are part of a much larger cloud-native ecosystem. Cloud Native Computing Foundation, CNCF, hosts numerous projects that complement Kubernetes. Service meshes, e.g., Istio Linkerd, add a transparent layer for managing inter-service communication, providing advanced traffic routing, security policies, and observability for microservices without changing application code. Observability tools, e.g., Prometheus, Grafana, OpenTelemetry, for collecting metrics, logs, and traces from your containerized applications to understand their health and performance. Secrets management, e.g., HashiCorp Vault, Kubernetes Secrets, tools for securely storing and distributing sensitive information to your applications at runtime. GitOps, a way to implement continuous delivery for cloud-native applications. It uses Git as the single source of truth for declarative infrastructure and application definitions, automating deployments via pull requests. Understanding these concepts will further enhance your ability to build, deploy, and manage modern applications. Your next steps: continuing the learning journey. Your Docker journey doesn't end here. The best way to deepen your understanding and keep up with the evolving landscape is through continuous practice and exploration. Practice hands-on, apply what you've learned to your own projects. Containerize a personal project. Set up a multi-service development environment with Docker Compose. Experiment with different base images and multi-stage builds. Implement resource limits and health checks for your containers. Explore orchestration, Minikube/Kind. These tools allow you to run a single-node Kubernetes cluster on your local machine. It's a great way to start experimenting with Kubernetes concepts like pods, deployments, and services without needing a full-blown cloud setup. Managed Kubernetes services. Once comfortable locally, try deploying to a managed Kubernetes service on a cloud provider, e.g., Google Kubernetes Engine (GKE), Amazon Elastic Kubernetes Service (EKS), Azure Kubernetes Service (AKS). These services manage the Kubernetes control plane for you, allowing you to focus on your applications. Dive deeper into Kubernetes. If you're serious about large-scale deployments, studying Kubernetes in more detail is a worthwhile investment. There are abundant online courses, certifications, and resources available. Monitor the ecosystem. Official documentation. The official Docker and Kubernetes documentation are consistently updated and invaluable resources. Developer blogs and news sites. Follow reputable tech blogs, e.g., Docker blog, Kubernetes blog, CNCF blog, major cloud providers' blogs, to stay abreast of new features, best practices, and industry trends. Online communities. Engage with communities on platforms like Stack Overflow, Reddit, e.g., r/Docker, r/Kubernetes, and Discord. Ask questions, share your knowledge, and learn from others. Conferences. Consider attending virtual or in-person conferences like KubeCon plus CloudNativeCon, DockerCon, or local meetups. Specialized tools and use cases. Docker Builds. For building multi-architecture images, e.g., for ARM processors like Apple Silicon or IoT devices. Test containers. A library for running database and other service containers automatically within your Java, Go, Node.js, etc. integration tests. Cross-platform deployments. Explore how containerization facilitates deploying applications across different cloud providers or on-premises data centers uniformly. A final thought: the container revolution isn't just a buzzword, it's a fundamental shift in how we think about and manage software. By embracing Docker containers, you're not just adopting a tool, you're adopting a mindset that prioritizes consistency, efficiency, and portability in your software development and deployment processes. You have now built a strong foundation in containerization. This journey has given you the knowledge to build, deploy, and troubleshoot applications in a modern, containerized world. Keep exploring, keep learning, and keep building. The horizon for technology is ever expanding, and your skills in navigating the containerized future are now well honed.